Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book, 3-volume series I wrote from 2019 to 2022 that's available on Amazon.com. Not going to advertise it any more than that because I have in a few other videos of mine. Anyway, just suffice it to say that I'm doing a video series on this book, on this series, in particular the first 2 volumes. And I'm up to section 3.4 of volume 1, which is on Fibonacci numbers and the golden ratio. And this is my 8th and final video on that section. And today I'm going to talk about how Fibonacci numbers and the golden ratio have been used in how they're used in nature and also how they've been used in art and architecture. So very important numbers and very let's just begin. So anyway, yeah, I'll first talk about how Fibonacci numbers appear in nature, and it turns out that flowers have, if you count the number of petals of most flowers, most flowers have a Fibonacci number of petals. It turns out. And actually, there's a good scientific reason for this. I don't go into this in my book, but it turns out this is the most economical possible arrangement of flower petals. It allows them to get the most sunlight as possible. If you think about a sunflower in particular, a sunflower, you guys have probably seen sunflowers. They have thousands of petals that's kind of spiral around the center. And if you count the number of petals going, they form 2 spirals, kind of a clockwise spiral, a counterclockwise spiral. I probably should have shown a picture here, but if you counted the number of petals going clockwise, say, you might get 55, and then if you did it counterclockwise, you get 89. Those are 2 consecutive Fibonacci numbers, and you might wonder why that's the case. Well, it turns out that this just happens. I'm not going to go into the details here, but if you want to arrange for flower petals in such a way that they maximize the amount of sunlight they can get, it just turns out that this is the most economical way to do it. You want each petal to go an angle of rotation of about 137.5 degrees, which is the full circle, 360 degrees divided by phi squared. Phi squared is also 1 plus phi. And if you do that arrangement, that will maximize the amount of sunlight you get for all the petals, and it'll also give you Fibonacci numbers going both clockwise and counterclockwise. That's all I'm going to say about that. You can prove what I just said, but I'm not going to bother with a proof. And I give several examples in my book of several different kinds of flowers that have Fibonacci number of petals. They don't all have Fibonacci number of petals. Most of them do. The ones that don't, I think, have twice Fibonacci numbers. Those are kind of rarities. And by the way, if you want to know why 4-leaf clovers are so rare, it turns out I think only 1 out of 10,000 clovers have 4 leaves. Most of them have 3 leaves. You might wonder why it's so hard to find 4-leaf clovers. The reason for that is because 4 is not a Fibonacci number, but 3 is. Anyway, I just thought I'd mention that. And that's how they occur in nature. That's just one way they occur in nature. That's the one I talk about in my book. There's other examples of Fibonacci numbers in nature involving pine cones. And I think if you look at like wings of certain insects, you'll see other places. Oh yeah, actually there is another place I talk about, the chamber nautilus. I talked about the golden spiral, I think, in my last video. And, you might think this is just a mathematical curiosity. But on the right, here's a picture of the golden spiral on the left, and I showed how to construct it yesterday. And on the right, you'll notice something that looks very, very similar, and this is a cross section of a chambered nautilus, the shell of a chambered nautilus. Because in case you guys don't know what chambered nautiluses are, they're crustaceans. They're kind of closely related to octopuses or octopi, if you like. They live inside this shell, and while they're growing, they grow this very beautiful logarithmic spiral pattern, and it's just because they're growing, the rate at which they're growing is proportional to their size. In other words, their growth rate is exponential. I'm not going to prove this. This is a very simple result of proven calculus. If you have something that grows at a rate that's proportional to its size, then it's experiencing exponential growth, sometimes called Malthusian growth. But chamber nautilus is a case in point. That's why their shell is shaped like a logarithmic spiral. And it's very, the slope of this logarithmic spiral is very close to the slope of the golden spiral. It's not exactly, but it's very close. And I'm not sure if that's just a coincidence or not. But at least I explained the mathematical reason why it's a logarithmic spiral, as is the golden spiral. Anyway, and then art. And here's a couple, probably the two most famous paintings by Leonardo da Vinci. I'm sure you guys have all heard of him. Probably one of the most famous painters of all time. Amazing guy, not just an amazing painter, but also an inventor and a mathematician, among other things. He was one of the pioneers of perspective, and there's a whole mathematical theory behind perspective, which was developed during the Renaissance, and he was one of the pioneers of perspective. Not only that, but he used the golden ratio. You might be surprised to learn this, but he used the golden ratio in both the Mona Lisa and in the Last Supper, his two most famous works. And you can see how he used it. I mean, if you look at a lot of people think that I think I mentioned this yesterday. A lot of people seem to think that the golden rectangle is the rectangle that has the most aesthetically pleasing aspect ratio. Well, guess what? Leonardo da Vinci used it in the Mona Lisa. If you measure various sizes, various proportions in this painting, like if you look at her face, for instance, if you measure, you can put a golden rectangle around her face. The ratio of the height of her face, in other words, the distance from the top of her forehead to her chin, if you divide that by the width of her face, that is the golden ratio. And Leonardo planned it that way, and he used it in several other places in this picture. And you can see where he used it. And this, he made a golden rectangle with several, iterations of the partitioning, which he can do infinitely times. He didn't do it infinitely many, but he did it enough for this picture. And got these beautiful proportions for most Mona Lisa. Um, and the Last Supper, he also used the golden ratio, golden rectangle extensively in the Last Supper. And you can see there's several golden rectangles presented in this picture, and this diagram showing where he used the golden ratio in that. I'm not going to explain it. You can just look for yourself to see where he used it. And it wasn't just Leonardo who was fascinated by the golden ratio. It's actually been used in architecture ever since ancient times. And I'm going to talk about the Parthenon first. The Greeks did know about the golden ratio, by the way. And I think it's pretty widely believed that they deliberately used the golden ratio in designing the Parthenon, which was their most famous temple. It's the most famous of the ancient Greek temples. I've never actually been to Athens. It's on my bucket list. I do really want to see the Acropolis and the Parthenon, and I'm sure that the Parthenon is a really fascinating sight to see. And one thing that's really fascinating about it was the use of the golden ratio. If you measure again the aspect ratio of the face of the Parthenon is the golden ratio. If you measure the rectangle making up most of the side of this. I don't think the pointed part counts, but if you just look at the rectangular portion, including the columns and the thing on top, I guess the part of the ceiling, except for the pointed part, that is a golden rectangle, to a very good approximation. And you might also be surprised to know that the golden ratio, I don't know if this was just a coincidence or not. I think it was probably a coincidence, but it turns out the golden ratio also comes into play in the architecture of the the Great Pyramids of Giza. And this is a really remarkable. I think this is kind of a mathematical coincidence. I know that people have put a lot of effort into analyzing the geometry of the Great Pyramids. Some people even think that they were created by aliens. I don't believe that. I think they were probably created by slave labor. I don't want to get into that, but one thing that's kind of remarkable about the Great Pyramids is that if you measure the two really famous irrational numbers appear in the geometry of the Great Pyramids: pi, and phi. And first, I'll talk about pi. So where does pi come in? Well, if you measure the ratio of the perimeter of the base, in other words, 4 times the side length, and you divide that by the height, that, to a very good approximation, is equal to 2 pi. And I don't think that was a coincidence. I mean, I think that it is known that the ancient Egyptians did know about pi. They had a very accurate estimate of pi, as a matter of fact, it was correct to within about 0.5%. And but phi also appears in the geometry. You might be surprised to know this. So where does phi appear? Well, let's look at the height of one of the faces. The Great Pyramids have 4 triangular faces, as you know. And if you measure the height of one of those faces, you take the ratio of the height of one of the triangular faces to the height of the pyramid itself. That turns out to be, to a very good approximation, equal to the square root of phi. And not only that, but if you also took the ratio of the I got to get this right. I don't want to mess up here. No, I think it's I take back what I just said. If you take the ratio of the height of the triangular face divided by actually, what I said was correct. The ratio of the height of the triangular face to the height of the pyramid itself is a square root of phi, but not only that, the ratio of the height of the pyramid to the half of the side length, in other words, the radius, if you like. Notice there's a right triangle in this picture. And this right triangle has, like all triangles do, it has 3 sides. It has 2 legs and a hypotenuse. The shortest leg is half the length of the base of the pyramid. You can call that 1 if you like, if you scale it right. And then you can call the height the square root of phi. It turns out the height is equal to the square root of phi times half the length of the base, or the length of the shorter leg of this triangle. And then if you take the length of the hypotenuse, that turns out to be phi itself. So, and you can show for yourself that 1 square root of phi is indeed a right triangle. That's pretty easy to see, because 1 plus square root of phi quantity squared, that's phi, is equal to phi squared. 1 plus phi is equal to phi squared. So that is a right triangle, and this also appears in the geometry of the pyramids. Of course, this isn't exact, because you can't you have two irrational numbers coming into play here. They're both approximations, and if we made a pyramid where the square root of phi and phi were exact, then it would turn out that the ratio of the perimeter to the radius, if you like, it's not exactly 2 pi, but it's only off by about less than 0.5%. I think it's something like 3.1448. I've actually done this calculation. So anyway, pretty remarkable coincidence. And I think it is just a coincidence that phi appears in the architecture of the pyramids, and also this kind of remarkable coincidence involving pi as well. Anyway, so that concludes my video today on the use of Fibonacci numbers and golden ratio in nature, art, and architecture. Also completes section 3.4 of the Math Lovers book. Chapter 3 as well. So next time I'll start on chapter 4, which is on imaginary numbers, and that should be pretty interesting. Anyway, thank you for watching. Long live math, and I'll see you guys next time.